Today, for the next 20-ish minutes, I will talk about what we learned from the D 5.1 deliverable that was from work package 5. And I will cover more the global eddy statistics, and then Steffi will cover more the polar regions. And yes, as Fraser said, it is submitted but not accepted. But you can find it on, if you want to download it to like scroll through or look at some other figures, it's on the ERIE project Zenodo. So you can have access there if you want. So to have just like an overview, the aim of the deliverable was to, in general, assess ocean mesoscale eddies in the, at that time, available ERIE runs, and to see which parts of the ocean are the winners and which are the losers in terms of eddy statistics and how the eddies look in each of the regions. So also focus in a little bit more. And the data available for us at the time. So in this deliverable, we managed to analyze ICON, IFS SPESM, and HadGEMS, and HadGEMS came in two resolutions. So we have HH, which is the high resolution model, and MM, which is the medium resolution. I think it's around 25-kilometer ocean resolution. We did not at that time have access to IFS NEMO, but it will. We are currently trying to write a paper, and there all of the ERIE models, coupled ocean models, will be analyzed. At that time, there were no historical runs, so we analyzed control runs of each of the models. And in this graph, can you see my cursor as well? Yep. So you can see the lengths of the spin-ups and how long the control runs were, and the dashed gray lines are the time periods which we took to analyze the eddies. So about the analysis, what we did is that we had the input data, which is all of the models that I mentioned previously. So the HadGEMS is here, HH the high resolution, and MM the medium resolution. And so for both of these, for all of these data, we had 20 years of daily data. We used quarter degree regridded fields, and we used only SSH for basically, I think, all of these analysis. And then for observations, we have Aviso provided eddy dataset, which is Meta 3.2, which is, I think, the latest one, which also covers 20 years. We selected for it to cover 20 years. Yes, so this is all of our available data and what we used. So then what we did with it is that first we calculated eddy kinetic energy as kind of like an overarching variable. And then for the majority of analysis, we used PyEddy tracker, which is actually the exact same package that Aviso uses to identify eddies and create their eddy dataset. So we use the same package and the same parameters. So it should eliminate some of the biases that might arise from that. And how PyEddy tracker works is that it just very simply looks at sea surface height anomaly field, which is filtered, and it draws circular round contours and calls it an eddy. And then to track it, it looks for similar eddies in size and area, like geographical area, and connects them through time, therefore tracking the eddy so you can see where it comes from. And then the data sets that we got is the eddy kinetic energy fields for all the models, and then the eddy datasets, which consists of kind of, you can think of it as two parts, which is one part, the kind of eddy round contour themselves, characteristics, which is like amplitude and size and geostrophic speed. And then if you couple them together, you can have track dataset, which has where you can see where the eddy was born and where did it die and how long did it live, for example. So this is kind of the data that we're working with. And I think we're moving on to, I think there's about 6 just bits of results that I found interesting and important that I wanted to share. So the first is eddy kinetic energy is like an overarching variable that makes sense to look at before looking at eddies individually. And here you can see eddy kinetic energy fields for here for Icon, for Aviso, and then the difference between two of them. So it's Icon minus Aviso. And at first glance, what you can see is that the eddy kinetic energy is the same order of magnitude, which is already pretty good. And you can see that there are similar features, which is that you can see the high eddy kinetic energy in the more stronger ocean currents, like Western Boundary Currents and ACC. And also that in the middle of the gyres, there is lower eddy kinetic energy, and it's similar, but if you look at the difference plot, you can see that also not only in Icon, but in all of the models, the eddy kinetic energy in the center of the gyres, or like in the lower energy areas of the ocean, was actually in models always lower than it was in Aviso, which could come down to the fact that Aviso sea surface height fields are quite interpolated, and this could introduce some uncertainty to the data. Also here in the difference plot, what you can see coming back to the stronger currents is that while the order of magnitude of the Western Boundary Currents is comparable, you can see that, for example, for here in Kuroshio, that it's placed not where it's placed in observation. So this problem still remains even with the high resolution models. And now to quantify a little bit what we saw, here is a regional mean eddy kinetic energy for a region. So the regions you can see in this map, I kind of bunched together all the eastern boundary regions, all the western boundary regions, and kind of did it in that combined way. And you can see here's eastern boundaries, western boundaries, and then the Southern Ocean and North Atlantic, which we will not talk much in this presentation, and we will focus on eastern and western boundary currents. And what you can see is that for eastern boundary currents, on average, the high resolution models, so those are all the bars that are not dashed. So the dashed bar or dashed whatever in all these plots is always the mid-resolution model from HAJMs. So from high resolution models, the difference between the observations and the models in the eastern boundary eddy kinetic energy is about 20%. So models have around 20% less eddy kinetic energy. But for example, Icon has only 3% difference, which is very good. Then for the western boundaries, the situation is quite different. And you can see that the models have 40% lower eddy kinetic energy in western boundary currents compared to the observations. So this shows that while globally it actually looks quite fine, regionally there are some stark differences. And we will come back to the eddy kinetic energy. We now quickly switch to the eddies themselves, which is kind of the main part of this deliverable. And here you can see just a qualitative view of how full tracks of eddies that were seen on one day, randomly selected one day, look. And they are so the lines are the tracks, and they are color coded by how long the eddy lives. So the darker the color, the longer the eddy lives. And the red dot shows you where the eddy was born. So you can see the propagation distance, propagation direction of the eddy. And here you can see the high resolution HAJMs map and the Aviso observational map. And you can see that in general, eddies are everywhere. And that, for example, the long-lived eddies come from the same places where the long-lived eddies come from in the observation. So those dynamics are captured. What you can also see is that the propagation direction is how we expect it to be from east to west generally, and then only in strong currents, it's west-east. So qualitatively, if you just look at this, you're like, oh yeah, there are some differences, for example, in the tropics, but we're doing quite well. Then to quantify this a little bit, if we just counted all of the eddies for 1 year, or like the average of all 20 years, then in this bar graph, you can see that just the number of tracked eddies in the models and in the observations. And incredibly, the high-resolution models capture 82 to 88% of the tracked eddies that we see in observations, which I think is a very good achievement. So this lower bar is for mid-resolution, and we will cover that a bit later. And so overall, the eddy number also seems rather okay. And what I want to do now is to compare what we covered first, the eddy kinetic energy, and what we covered now, which is the number of eddies, and see how that differs regionally. So here, if you need a reminder, here's a little map with the regions. So we saw this, that there is that the difference between the high resolution models and observations is larger in western boundary currents for eddy kinetic energy. So there's larger discrepancy, while the eastern boundary currents are doing a little bit better. If we look at the eddy number, so here it's mean eddy birth, which is a way to capture the tracked eddies. It's mean eddy births because if I would take eddy instances, it would cover every eddy as many times as it occurred in its lifetime, and I think this is a better proxy for that. But I checked, and the results are essentially the same for whatever eddy number proxy you would like to choose. I just chose eddy birth. And here you can see the mean eddy birth for all models and observations. And what you can see, interestingly, is that now in eastern boundary currents, there is 38% less eddy births than in observations. But in the western boundary currents, the difference between observations and the high resolution models is only 20%. And I think this very interestingly, like, it shows a nice difference between different eddy metrics and tells you that while eddy kinetic energy is in general very useful variable to look at when you want to assess mesoscale variability, it might not capture exactly round, coherent mesoscale eddy numbers or statistics or dynamics, because you can see here that the eddy kinetic energy bias is actually not the same bias that we see in the number of eddies. What might be the reason behind this? We're only now starting to think deeper about it. So if you have any fun ideas, do reach out and talk. So in western boundary currents, the eddy kinetic energy, this difference might be higher because the major component of the eddy kinetic energy in western boundary currents are the non-eddy components, so the jets and the waves, and so the non-eddy stuff. So that might be the reason that causes these huge biases, and as we can see, not the eddies so much themselves. So this was another, I really enjoyed this part of the deliverable. And then I want to touch upon eddy lifetime, which I actually also covered in the GA in January. But so this is a histogram of eddy lifetimes. So on the x-axis, we have eddy lifetime, and on the y-axis, the number of eddies that lived this long. So here are a lot of eddies that lived for a short amount of time, and here are a few eddies that lived for a long amount of time. And you can see also in this kind of magnification walk of the plot that the observations tend to have more short-lived eddies and less long-lived eddies, as evident by this number of by this yellow line being below all the blue lines. And so yeah, the eddies in models live longer in general than they do in observations, and it's consistent across all models. So there should be some explanation that is common to all of them. So one of the reasons that could lead to eddies being longer lived in models is simply that the observations are not perfect. Because the satellite altimetry fields are so heavily interpolated from the swaths, that it might be easier in this interpolated field to interpolate and miss eddy for a few days, therefore kind of cutting the eddy in half where it should be one long eddy, but because of how it's interpolated, it actually misses the eddy, therefore it creates more shorter eddies. However, we might be missing eddy decay and like mechanisms for the eddies to die, because some of these mechanisms could be sub-mesoscale, and our models do not include those. Therefore, it could be that the eddy lifetime is longer in the models kind of artificially because we are missing some of the processes. Yep, and then I want to quickly show you how we're doing well also not only on the pure number of eddies, but also the characteristics of eddies, so the quality of the eddy that you get. And what you can see here is the mean radius of eddies in Icon and Aviso, and here is a zonal plot of it. So here the different colored lines are all of the models, and the black line is the Rossby radius. And what you can see in the fields is that the Rossby, that the eddy size is very, like, it's well represented, and you can see some smaller features, that it's larger in stronger currents, and then that the eddies are smaller in the middle of the gyres, and just some general features are well captured, which is also visible in the zonal plot, except for the poles, which Steffi will cover, and also it diverges more in around the equator. However, in general, it's doing rather well. The only exception is this dotted line, which is the line for medium resolution model. So you can see that the eddies are larger. And this brings me to the last point, which is the gain that you have between medium and high resolution models, which was not really the main aim of the deliverable, but we touched upon it. And so HadGEMs coming in high resolution and medium resolution was an excellent opportunity to explore this. And here I will show you side by side the high resolution and the medium resolution HadGEMs. And here is the eddy occurrence instances. And you can see that it is so that the medium resolution captured only 55% of what was visible in observations. And if you remember, the high resolution model captured, I think the HadGEMs was closer to 90% of the number of eddies in the field, which is a great improvement, which is a great improvement in like a sheer number of eddies that you can analyze. And moreover, you have not only an improvement in the number of eddies that you have, but also in the quality of eddies that you have, because we can see here that the eddy radius in the medium resolution model is around 20% larger than in the high resolution models or the observations. And we can see in the previous slide how the high resolution models are very, very comparable to the observations. So this brings me to conclusions, which is that very encouragingly, we have a well-represented eddy field in all of the high-resolution EERIE models that we analyzed, and that there is a significant improvement going to high resolution if you want to look at eddies themselves and eddy statistics. However, there are still these regional differences where some regions are better represented than others. I think it will be also evident in Steffi's presentation, and that there are still challenges about this model evaluation, which is that we are unsure about whether there are some downsides to the observations that we are using. But that's what you kind of have to deal with when you do model intercomparison. And yeah, I think that is it from me. Thanks for listening. And if you have any burning questions, you can ask now, or you can also wait until Stephy's presentation.
Thank you, Stella. So yes, any burning questions, or are we good to move on to Stephy's presentation? I see Matthias has his hand raised, so.
Yeah, hi. Great, thanks. Great talk. Just a quick question, because you said on that maybe the observations may also not be as good. Do you see any sort of trends over time in that? I mean, in the SST products, we see that the eddy resolved eddy features get much better. Sorry, you don't hear me well? Oops.
You lagged a little bit and I missed something.
Okay. Sorry for that.
No, that's fine.
That's better now? Maybe I try to speak
you can try.
Slowly. Okay. In the SSD products, we see that the eddy features, resolved eddy features, get much better in the more recent period, as I suppose the satellite products get better. So I was curious if you see this also for the SSH, and maybe the statistic you get more eddies in Aviso in a more recent period, or things of this kind. And maybe this would give you an indication of how the quality of the observations is compared to the models.
Yeah, I think that's a very good question. So I personally haven't looked at it, but there's this paper by Martinez Moreno, I think 2022, and they looked at sea surface height from satellite altimetry and analyzed the whole available period, which I think at that time was around 30 years. And they did see a trend in eddy kinetic energy, number of eddies, and stuff like that. However, it's very hard to interpret whether that's because of climate change or whether that's because we have more satellites. So I think it is very inconclusive also in that study where this kind of trend is coming from.
Okay, thank you, Stella. So next up, we have Stephy, who is Stephy's a postdoc at UC Louvain, for those of you who haven't met her. And yeah, she's going to be talking to us about eddy statistics in the polar oceans. So over to you, Stephy.
Thank you, Fraser, and thank you, Stella. Are you able to see the screen? Okay, perfect. So thanks everyone for sticking around. And as Stella said, this is part of the EERIE deliverable D5.1. And this is actually a continuation of what Stella has done. And we've used consistently the same data set. So we're just focusing on the polar regions. So before we move into the statistics, just a brief overview that what we do here with the eddy identification and tracking is quite relevant to the work that we conducted UC Louvain for the work package 5, where we are doing the evaluation of ocean mesoscale processes and their interaction with the atmosphere and sea ice. So after doing the tracking, eddy identification and tracking, we then try to build composites and try and understand how the local eddy influences between the ocean and the sea ice, and also between the eddy and the atmosphere. And so doing this statistical or assessment of how the eddy characteristics in the polar region then plays a role in understanding how the different models are reproducing the key processes. So yeah, we're building composites like that. Okay. So now Stella was focusing mainly on the global evaluation, where she was not really focusing on the polar regions. And in a lot of eddy studies that is done globally, the polar regions are quite challenging to study, mainly because it's hard to get the data because usually due to the smaller radii and sea ice cover that blocks the observation. There's not much data that is available for studying eddies in the polar regions. With the EERIE models, we have the eddy-rich and eddy-permitting conditions where we are able to have the eddies and we can analyze the dynamics. It is still limited in certain conditions where it's approaching the poles or if it is shallow shelf regions. And then in this deliverable, we are evaluating it against AVISO, while we are already aware that there are certain limitations with using AVISO in the polar regions. And before I go into the results, I also want to acknowledge there are two key aspects that we overlook or accept as limitations. One is that in the polar regions, because of the sea ice, the friction dissipates a lot of surface propagating eddies. And so in the subsurface, you might have a much higher population of eddies. So if you're really interested in how much eddies are present, you're better off looking at subsurface eddies. But since we are looking at eddy interaction with the ice and with the atmosphere, we still have to look at eddies that are present at the surface level. So we continue with the same eddy identification as with the PyEddy tracker using sea level anomalies. And also when we're comparing it with AVISO, it is not really ideal because it does state that beyond 66 degrees north and south latitude, there are a lot of uncertainties. It's only relying on one single satellite data, and also under ice and in the shallow regions, there's a lot of uncertainties. So keeping that in mind, we still use AVISO data because we get the circumpolar or like the whole region for both poles. We do have the product by Ogier et al. In 2021 for Southern Ocean, but we don't have a counter product for Arctic. So I know that there's a lot of panels here, and it would be difficult to say all the aspects in one go. I'm only focusing on a few key points, and the rest of it you'd be able to find in the deliverable. So when we look at the eddy amplitude, you have the AVISO products at the right-hand corner. And then when we look at the different EERIE models, we find that most of the strong western boundary currents and the ACC are produced with good fidelity. And the strongest one is for the high resolution Hadjim model. Yeah, and the medium resolution model does underestimate the eddy amplitude a little bit. Sorry, I might be going a little fast here, but hopefully you will be able to find this information in the deliverable as well. When we look at the eddy radius outside the sea ice zone, so here in the previous figure as well, I'm marking the sea ice extent in the winter in red and summer in blue for the respective models and also for observation. So outside of the sea ice zone, the models tend to produce the eddy radius in good fidelity, or it's actually not too bad. But one of the main things that we noticed was some of the models seems to overestimate, mainly the Hadjim model in the medium resolution seems to overestimate the eddy radius in the polar oceans. And we don't know why that is happening, but it is one of the issues that we noticed. And then when we look at the eddy birth and death frequency, compared to the observations, the frequency is slightly lower in the models. And also the AVISO seems to overestimate the birth and death frequency close to ice edge. And we have a hypothesis that might be because since AVISO cannot observe eddies under the ice, it might be considering the ice edge as a boundary where eddy death and birth is happening, but in the models it doesn't have that issue. So that might be one of the reasons that the models do not overestimate in these regions, but AVISO does. Now I think we're going to the statistics of eddies under the sea ice, and here I've actually done this assessment with 5 years of daily data for eddies that we identify, and then we compute the total number of eddies and also gather the area, amplitude, and radius, and all those features for that, and then create this annual evolution. So first I have the evolution of sea ice area for the different models and also observations, which is OCSAF. And then when we look at it, most of these parameters do actually change along with the sea ice growth and melt, and some of it is quite sensible and expected, because if you have more sea ice area, then you have more eddies under that, or the area of eddies under sea ice also will increase. But then also we check how the amplitude and radius changes, which can also have an impact in a geographic way, but also can be varying in terms of how the thickness of the ice changes and other oceanographic conditions like stratification changes and so on. So this actually allows us to see what is the baseline and then continue our analysis in composites and so on. When we compare amongst the different models, we actually see that icon model, which is the teal color, it's actually producing a very high number of eddies. So there's a lot of eddies, and also it is one with a very small radius of eddies. So the densities, eddy density is higher, and it's also having lower ice cover in the Arctic. And overall, it seems that the Hadjam models have much less eddy count, and then the anomalous amount of eddy radius that happens in Hadjam medium resolution does show up again. And then when we go to the Antarctic, the seasonal cycle and the other characteristics of eddies following the seasonal cycle is much, much stronger, which is quite encouraging for our analysis. And again, the Hadjam models seems to have a lesser eddy count. And again, the higher radius and all these similar aspects. Most of the parameters seems to be following the seasonal cycle a lot stronger when it comes to the Antarctic. Yes, and also interestingly in the Antarctic, the amplitude and radius, except for the medium resolution Hadjam, seems to be converging in winter, and it's actually something that is new for me and something that might be interesting to look into. And now the previous figures was for the total eddies, so we're not differentiating whether they are in the edge, ice edge, or in the ice pack. This is for the total eddies. But now we differentiate the eddy statistics that we have in the different categories of sea ice, and this is for some reasons where in the eddy ice interaction dynamics, we do some studies have shown that regarding depending on whether the ice is mobile or immobile, whether it's a pack ice or if it is broken ice flows that is just moving around, the dynamics can change. And also depending on the location where the ice is, the impact of the eddy. So if it is a warm core eddy or a cold core eddy, the impact of that eddy, whether it's melting more ice or freezing more ice, all of those factors can change. And so it's important that we do not generalize all the eddy effects and just take an average. And it's more helpful to identify in which categories and in which regions the processes are happening. So we mainly make 4 categories. We have the ice category, where the CS concentration is greater than 70%. Then the marginal ice zone south is south, where the CS concentration is between 40 to 70%. The marginal ice zone north, where the CS concentration is between 10 to 40%, and then also the no ice condition where it's less than 10%. And sorry for the plot slide with the lot of figures coming up. So here on the left-hand side, you have the Arctic statistics for the eddy amplitude, and it's for 4 of the EERIE models. And then again, it's following the seasonal cycle on the x-axis. And when we look at it, we do see that the eddy amplitude for the marginal ice zones are much higher than in the pack ice, or the inside the pack ice, the variability is much lower than what happens in the marginalized zone. Although Icon model does not seem to have a huge variability in that. Perhaps the smaller eddy radiuses and the higher density has something to play there. And then when we look in the Antarctic, please ignore this high jump where the number of eddies are much lower, and this variability is something that we ignore. Again, we see that the peak is higher in the sea ice maximum, when we expect the ice cover to be at the highest, and also moving into the regions of high eddy amplitude. And again, in both poles, you have lower variability in the amplitude under the ice pack. Yeah, so now when we look in the radius, again, on the left-hand side, you have the Arctic Ocean. And in the Arctic Ocean, one of the interesting things that we notice is this increase in the radius in summer. And that was a bit counterintuitive for me. But then the hypothesis that I have right now is that in winter, when the ice expands and moves into the coastal shallow regions, you have more eddies that might be of lower radius. But then as the ice contracts and moves into the central Arctic region, then you might have eddies that are larger in the deeper Arctic Ocean region. So that might be the reason that we have this jump, which we do not see in the Antarctic. Geographically, these two regions are quite different, so that can be a difference, a reason. And in the Antarctic, interestingly, a lot of the model seems to converge their eddy radius in winter, which is again something that I need to think about, where one might expect that, say, in winter at the ice edge or marginal zone, there might be larger eddies, but it still needs to be tested and checked with other data as well. And then I think that that's mostly the end of these statistical assessment. And so we did actually test or do evaluation of the eddy statistics in the polar regions. And we compared it against Aviso, acknowledging that it's not entirely the correct way to do. And then for the EERIE models, we checked the key characteristics like amplitude, radius, and the regions of high birth and death frequency. And the model seems to have reasonably good fidelity. There are a few issues, just like I said, about the very large radius in the Arctic Ocean for HARGEMS, or a few areas where that might be an issue. And then when we looked at the eddy statistics or the eddy characteristics under the sea ice in the total mean, we see that is following the annual cycle of the sea ice in that region quite well. And then we also looked at that further into the ice categories. And then when we look into that, we see some of the behaviors that are consistent with what we expect from theory, but also some that are a bit interesting, that needs more analysis. And overall, I find that this analysis does show that EERIE models are producing eddies quite well in the polar regions, that we can use it for more eddy dynamics analysis. And I think that's the end of my presentation. Thank you.
Okay, thank you, Steffi. So yeah, so now I guess it's time for us to, lots of virtual rounds of applause. happening. But yeah, I think that now it's time for us to jump into some more in-depth discussion. So does anyone have any questions? Feel free to raise your hands. Yep. So Markel, you were first. So over to you. I see your hands up.
Thank you. Very nice talks. Thank you. I'm not an oceanographer, so I don't want to read the static thing, but I wanted to ask maybe if you know about if there is an alternative to AVISO, or somehow maybe a reanalysis instead of satellite observations or something, some model running with ERA5 winds, but able to produce eddies, because normally if we are doing multi-decadal simulations, you will expect that there is someone doing a reanalysis too, but I don't know. It would make sense for me.
I can answer that. I think currently AVISO is the best that we have, because doesn't reanalysis take into account AVISO? Isn't it one of the products that goes into?
I don't know about ocean analysis. I just know about atmospheres.
Itself.
I do think
I'm
so.
also not sure. I don't work with reanalysis. But I think it feeds into ERA5. Not sure, but there's, for higher resolution, there's now the SWOT, WOT campaign, which has high resolution surface height and like surface altimeter data. However, it provides only level 3 product, which is still in the swaths and not in full fields. And I am not, unfortunately, in the correct field to make it into full fields. Like I don't want to spend time doing that. So there would be a better alternative if I was a remote sensing scientist, but I am not. But if you have any other ideas how to look at eddies, then I would love to. But I've never, usually in the field of mesoscale eddies, if you need observations, everyone is using AVISO. I rarely see anything else.
Okay, yeah, I don't have, sorry, these ideas. I just,
no, that's fine.
But was curious to know if there was an analysis. But
I'd like to make a comment, because I think when I did mention that AVISO was not a good product for comparison, it's only for the polar regions. I think when you are looking at the lower latitudes, I think AVISO is still a very good product to do. It's just that it's not the most ideal thing for polar regions, but there isn't really much that exists except the paper that the work that I mentioned, that is for the Southern Ocean. There is a product that they created for 7 years by Orgia and others. So there's one product for Southern Ocean, but there's no counter product for Arctic. That's why we still use AVISO, so it's easy to compare and have those, polar projections for both poles.
Nice. Okay.
thank you.
Nikki, do you have a point or a separate question?
No, that's a
It's
question.
related.
I mean, a point. Nothing.
Okay.
Well, it would be nice if reanalyses were to cover mesoscale eddies, but they don't. My question is actually to both of you, is not so much about the deliverable itself, which, by the way, great. You both of you did a great job, but about subsurface eddies. I mean, Steffi, you mentioned that. I mean, and so the question goes first to you, but then I think what also curious Stella has to say about that. I mean, is there a good way to assess subsurface eddies? I mean, is there a way how we can say something about that? I mean, there are now, people have tried Argo floats to look at essentially vertical structures and things like that, maybe also high frequency glider surveys. Yeah, so any way that we can say anything about subsurface eddies?
So if I have to answer, Yeah, I just did actually check the methods in some papers before I made this doc as well. So I know that they're looking at vorticity and also velocities to identify the subsurface edge and characteristics. And I'm pretty sure you're aware of that too. But then in the polar regions, I think there are some moorings and other observation platforms that gives such data. It won't be too widespread. It will be more localized. That's how I would think about it.
I have actually looked quite a lot into 3D eddies. The problem for me is that there is, what do you consider eddy contour? Because you need to choose a variable and then just stick with it, and there needs to be some reasoning. So actually what Nate, who was in our group, suggested to do is to look at Okubo Weiss and do it in all levels. I already have a code for it, and that has been done previously. Yeah, as Steffi also said, there are some studies that use potential vorticity. There are velocity fields, but yeah, it's the question of where do you say, where's the boundary of the eddy 3D? Is it the temperature anomaly? Is it whatever? And I think the eddies can wildly differ depending on what you choose. That's why I haven't thought about it much, because it's so, I think, kind of subjective on what you choose.
Well, I think, I mean, the same is to a certain degree true also for surface detection. I mean, depending, of course, if you use Okubo Weiss or Pi-eddy tracker, I mean, we see differences. But I think subsurface, I agree. I mean, it's getting worse. But I think, nevertheless, I mean, it would be interesting now we have such a good perspective on the surface to really look below the surface, so that because that's a big step away from the observations, but really where the models can bring in a lot of extra information, and it's an area that we haven't quite learned so much. Well, that's great. Thank you.
Malcolm, do you want to go next?
Yes, thank you. Thank you both. They're both really good talks. Stella, I know I've kind of asked this before, and it relates a bit to that earlier question. So you said with the lifetimes that you found that there's this kind of key uncertainty. Is it that the observations don't give us the right lifetime, or are the models giving too long a lifetime? And we had the similar thing with Sophia Morton's paper a few years ago as well. Do you have any thoughts on actually how we take that forward? Because I know you, as you say, someone could do the kind of follow the satellite tracks round and maybe do something, and that could do something. But do you have any thoughts on how else we could take this question forward? Because it's important.
I don't have a good answer for you.
No, I understand.
Yeah, don't have a good answer to that. I'll think about it and try to come up with something of how to look into that. Yeah. And more from the side of assessing the model rather than going into remote sensing and doing all of that, because that's maybe where we could, the next, the person presenting, I think, should be much bigger expert on that, on sea surface height. Yeah, no good answer, unfortunately.
I mean, do you think, so we've got what, a year or two of the SWOT data, which is somewhat higher resolution. I don't know if it's any much different spatially. Could that, if we had compare those two different data sets, could that tell us something? Even, you know, even with 2 years, at least you could compare the numbers or something between the two.
Yes, that could be one way. Yeah, that could help to answer the question of whether Aviso is splitting the eddies, especially if you can look at the time that's overlapping between the SWOT and Aviso to actually look at time frame, not rather than a climatology, to look maybe at some specific cases and following specific eddies and finding out if that's the case. Maybe that could be a way to go.
Okay, great, thank you.
Okay, and once you've asked your questions, if you could lower your hand, unless you have another question, that'd be helpful. Thomas, I see you've got a hand
Yeah,
raised.
thank you very much. I mean, two very nice presentations, which are based on a very nice deliverable, I have to say. So that's very good. I mean, my question is a little bit based on the discussion I just had before the seminar started here with Rohit, and this was a little bit about how long do we need to run our control simulations for, you know, when it comes to estimating drift of the model. And I know probably in terms of eddy characteristics, we really haven't looked into drift, right? But as soon as we start in sort of being interested in the climate change of eddy statistics, how do eddies change in a warming world? We would like to compare that to a drift in a coupled run, because, you know, if both change in sort of in orders of magnitude that are comparable, then, you know, we have an issue and we certainly need a control in order to make a statement. But to me, it's not entirely clear. And there may be a difference between surface eddies and subsurface eddies, you know, how they drift. But I'm wondering a little bit, you know, for those people having their hands on the data, whether perhaps we can learn a little bit about the drift of eddy characteristics in the simulations that we have right now, because I guess it could help us in terms of the priority we should be giving to extending control simulations versus making projections longer versus giving high priority, you know, to long ensemble members and stuff. Just wondering, right? Probably you don't have answers, but it's just a thought given what I've just discussed with Rohit.
So the only answer I have is the number of eddies. So in the deliverable, there is a time series of the number of eddies in each of the models for the 20 years of control that we analyzed. And there seems to be very, very little drift, except for FESM, I think. For FESM, there was a little bump somewhere, I remember. But in general, for the models and observations, there's very little, maybe 5% change in the 20 years, like wobble. Yeah, but that's in the control run.
Yeah, I mean, it would be
Not yet
nice if
looked
someone has
into
some
historical.
time, you know, to look at maps as well. You could have underestimation here and overestimation, you know, drift in opposite directions, which then in sort of an integrated plot you wouldn't see, just sort of to be on the comfortable side. And again, if some groups actually are looking at sort of deeper layer eddies, you know, there's some interesting discussion in the scientific literature going on as well, just for us to get a little bit of a flavor of whether there is, you know, something to be, you know, not concerned about, but something to be aware of, right?
Mm-hmm.
Just say I started to, and then I found a bug in in how the tracking did the dates. But what I want to do with my historical run is to do the 20 years, kind of 1850 to 1870, and then something around 1900, and then something around 1950, and then something around 2000. So it's not really the drift, but is there anything significantly different in the eddy statistics in those? Because obviously with the longer baseline, and so we can at least see whether in our model there is actually any change in the eddies over time. Because if there isn't, then there's no, we're kind of not looking for a signal. And yes, the drift might still be important, but if there's no signal, then there's no signal. So that's something I need to go back to, because yeah, it was messing up the times before, but isn't now. So,
are there any more questions through our speakers? No. In which case, I guess this is good timing because it's just gone 3 o'clock. And that means science hour is over. So just a reminder that next month, I've got the date now. Next month, there is no science hour. The next science hour is on the 15th of September at 2 o'clock. And as a reminder, we'll be getting some simulation updates and we'll be hearing from William Lovell about sea sea level variability. So thank you very much for coming. Thank you to both our speakers, and looking forward to seeing you in a couple of months. Have a good summer.